Chapter 7, and it starts with the fundamental counting principle. So here we are in your final chapter of high school math. And we're going to finish off by learning how to count. Isn't that great? Kind of like back when you started math. Way back when you learned how to count. But this is a different type of counting this time. We're not going to learn to count the number of boys in the class, for example. We're going to learn to count things like the number of teams of 3 we can make if there's 30 kids in the class and we want to make teams of 3. How many different possible teams of 3 are there? That's much more complicated counting. So the basis of all this is the fundamental counting principle. And what the fundamental counting principle says is if there's m different objects in one set and n different objects in a second set, then the number of ways of choosing one object from each set is m times n. So for example, say we have 2 boxes, and in the first box we have 3 marbles, a small one, a medium one, and a big one. And in the second box we have 3 triangles, a small one, a medium one, and a big one. And we want to pick one thing from the first box and one thing from the second box. How many different combinations are there? Well, you could start listing them. You could go, oh, I could get the small one in the small triangle, or the small one in the medium triangle, the small one in the big triangle. And it wouldn't take too long. You could do that. But we're going to do much more complicated questions. So the way you need to do this is by using the fundamental counting principle. And the fundamental counting principle says, well, in the first box here we have 3 choices. In the second box here we have 3 choices. So total there's 3 times 3 is 9. There's 9 different possibilities if we're going to pick one from the first box and one from the second box. Okay, let's do some more examples like this. How many even 2-digit numbers are there? Okay, so 2 digits. First of all, how many digits are there in our counting system, our number system? There's 10, right? That's why it's a base 10 system. You might think, well, there's only 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the other digit? 0. Okay, how many digits can fit in the first spot, the 10 spot? Can they all fit in there? No, there's one number that can't fit in there. You can't put a 0 there because we need a 2-digit number, and we're not going to count 0, 3 as a 2-digit number. It's really just 3. So you can't put 0 there, so that leaves us with 9 possibilities in that first spot. How many numbers can fit in the second spot here? Well, it needs to be an even number. That means it has to end with either 0, 2, 4, 6, or 8. So we could have 5 different numbers in that spot. How do we get the total number of different numbers? Multiply those together, 45. There's 45 2-digit numbers. Again, you could probably sit here and list them all and it wouldn't take you too long, but we want to learn how to use the fundamental counting principle because the questions are going to get very complicated. How many 2-digit whole numbers can be found using these digits if repetitions are allowed? Okay, so again, we have 2 digits, and the first number here it has to be 2 digits, so again, you can't have a 0 here. No 0. So this is the same as above. Oh, wait a minute. No, it's not, because there's not 10 digits. There's only 5 digits, and we can't put 0 in there. So it leaves us with the 2, the 4, the 6, and 8. There's 4 possible digits here. Repetitions are allowed, so it doesn't matter if it goes 4, 4 in this case. So how many numbers can we put in the second spot? We can put any of those digits in that spot. Right? So any of those 5 can go in there. 4 times 5. There's 20 different numbers that fit that pattern. How about if repetitions are not allowed? Okay, well, again, in that first spot, you can't have a 0. So there's 4 different ones that you could use. The 2, the 4, the 6, or the 8. How about in the second spot? Repetitions are not allowed. So you already have picked one number to go in the first spot. Remember, it doesn't mean it's a 4. This doesn't mean the first number is a 4. This means you've picked one of these 4 numbers. Now, for the second number, what's true? What do you know? It means you can't pick that same number again. So, for example, if the first number here is a 2, in the second spot you cannot have a 2. So how many numbers are left to pick from? Well, there's only 4 left. You add in the 0, you're allowed to pick the 0 now, so you go up to 5, but you can't pick the number that you picked in the first spot, so you take 1 off, you're back to 4 again. 4 times 4, 16 possibilities. If you don't understand, think of it this way. The difference between the 20 here and the 16 here is 4. What are those 4 numbers? The 4 numbers you're not allowed to have are 22, 44, 66, and 88. Those are the 4 we had to remove, and we didn't have to do it by listing them like I just did here. We could use the fundamental counting principle. Okay, the last one. BC license plates are made up of 3 numbers and 3 letters. How many different license plates could be generated in this model? Okay, so the first 3 spots, these are all numbers, or maybe it's letters actually. I think it changes in different years. Anyway, who cares? We got, whoa, what's that? That's horrible. We got numbers and we got letters. How many numbers could go in the first spot? How many digits? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How about the second spot? 10. Third one, 10. Doesn't say anything about repetitions. Repetitions allowed, I guess. So 10 times 10 times 10, but we keep going. How many letters? You can put any letter. How many letters are there? 26. How about the next spot? 26. Next one, 26. Multiply all that together and you'll get your answer. The answer will be, once you multiply that all out, 17,576,000. So I hope this gives you an idea about how you want to start using the fundamental counting principle. I don't want to sit here and list 17,576,000 different combinations. That's too many for my liking. Okay, so that's that. The second part of the lesson today is tree diagrams. Now, believe it or not, we did tree diagrams together. If you're in my grade 8 class, I remember doing them together. They're a good way to visualize and count the number of possible outcomes. Now, that's a long time ago, grade 8, and you may not recall them. I remember in grade 8, a lot of you found them very difficult. This will be interesting for you, I think, to see how different things are 4 years later. In grade 8, you found this very difficult. I bet now you're going to say to yourself, huh? What was difficult about this? Maybe not. Maybe it'll still be difficult, and that's fine if it is. You'll get it. So, a room has 2 lamps. Each lamp has 4 settings: off, low, medium, and high. We want to know how many ways are there to set both the lamps. So the way that people do this and get it wrong all the time, like when I teach my grade 8s this year, if I'm teaching grade 8s this year, the way that most of them will do this, which will be wrong, is they'll start at a dot. That's how you always start a tree diagram, with a dot or point, whatever. And you can either work down like this, right, working downwards, or you can move across the page. I usually work across just because it seems to fit better on the sort of paper we use. So I'm going to work across the page, and what a lot of people do is they say, oh, there's 2 lamps, so I'll make my tree diagram go lamp 1 and lamp 2. But that's not how you do it. This is completely wrong. Okay, don't do that. What you do is you consider one of the lamps at a time, one of the objects at a time. You don't make a tree diagram and go lamp 1, lamp 2. You think to yourself, okay, there's 2 lamps. I'm going to consider the first lamp. Now, when I'm thinking about the first lamp, what are the settings that that lamp could have? That first lamp could be at a setting off. It could be at a setting low. It could be at the setting medium. And it could be at the setting high. Okay, if it helps you picture this, I will write below, this is lamp 1, or one of the lamps, whatever. Now what you do is you think, okay, let's say that that first lamp was off. Now I'm going to think of the second lamp. What could the second lamp be? The second lamp could be off, low, medium, high. What if the first lamp was low? What could the second one be? It could still be off, low, medium, high. How about if the first lamp was medium? It could still, the second one could be off, low, medium, high, and in this final case, when the first one's high, it could also be off, low, medium, high. All this stuff here is the lamp 2. So when you want to know what all the different possibilities are, where you look is right out here at the end, and you just count out how many things there are at the end here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 possible outcomes. Okay, a couple things about that. One, what do all these things mean? So for example, if I asked you, what does this mean here, this 0 right here? Well, what this means, if we follow it back, this means, like, to get back to the starting point, we'd have to go this pathway, right? So this means when lamp 1 is on medium and lamp 2 is off. What does this one mean right here with the L? That means, if I go back this pathway is the first lamp is low and the second lamp is low, right? These are all the different pathways. There's 16 different pathways. Now, some of you are probably saying that was so unnecessary. We could use the fundamental counting counting principle. How many settings are there for the first lamp? 4. How many settings are there for the second lamp? 4. 4 times 4 is 16. What a waste of time. I'm never going to use tree diagrams. Too bad. You will have to use them sometime, because sometimes you can't use the fundamental counting principle. A question like this is very, very difficult to use the fundamental counting principle. So let's see how we could do this with a tree diagram. How many ways are there to roll a 4 or 7 total? Like, I don't just mean rolling a 4 or rolling 7. First of all, it's impossible to roll 7 with 2 standard dice. Standard dice, 1 to 6, right? Okay, so again, you're not going to go dice 1 or die 1, as it's properly called, and die 2. That's not what you're going to do. That's wrong. You are going to think of the first die. You're going to say to yourself, the first die, what could it be? Well, it could be 1. I'm going to try to spread this out. 2, 3. I don't think I did a very good job. 4, 5, and 6. That's the first die. Now the second die, if the first one's 1, what could the second one be? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, or 6. If the first one's 2, the second one could still be 1, 2, 3, 4, 5, 6. Basically, you're just going to write 1, 2, 3, 4, 5, 6 for all these positions, aren't you? 1, 2, 3, 4, 5, 6. It's very hard to fit this in. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we haven't answered anything yet. Now we have to look for how many ways are there to roll a 4 or a 7. Well, how could you get a 4? You could get a 1 and a 3, so that's one pathway right there that works. How else could you get a 4? A 2 and a 2, a 3 and a 1, a 4 and a 0. Oh, there's no 0 on that. The 5 and that? No. Okay, that's it. That's all the ways you can get a 4. How many ways are there to get a 7? You could get a 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. So how many ways are there to roll 4 or 7? Just count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 ways. By the way, we don't teach it to you anymore, but we used to teach probability at this time of the course as well. If you want to know the probability of rolling a 4 or 7, you take these number of possibles, 9, and divide by the total number. How many total pathways are there here? 36. So you get 9 over 36, which is the same as 1/4 or 25%. That's the probability of rolling a 4 or 7. But the good news for you is we don't have that in our curriculum anymore. They took that out for some reason. Not totally clear why. That will be it for today. Nice and short. Enjoy the fundamental counting principle, the power of the fundamental counting principle.